Welcome to Quantum Realms Explained. Today, we're diving into one of the most mind-bending concepts in quantum physics, De Broglie's hypothesis, and the fascinating idea of wave-particle duality. Have you ever wondered if everything around us, from the smallest electron to the largest planet, might not be as simple as it seems? What if particles can behave like waves, and waves like particles? For centuries, classical physics clearly separated the world into distinct categories. Particles were discrete entities with definite positions, and waves were disturbances that spread out. But at the turn of the 20th century, the quantum world began to challenge these rigid definitions. In 1924, a brilliant young French physicist named Louis De Broglie proposed a revolutionary idea that would forever change our understanding of reality. He hypothesized that just as light can exhibit both wave-like and particle-like properties, matter itself might also possess this duality. To understand De Broglie's genius, let's first quickly recap how light behaves. Remember, light was once thought of purely as a wave, explaining phenomena like diffraction and interference. However, Einstein's explanation of the photoelectric effect showed that light also behaves as discrete packets of energy called photons, acting like particles. So light has this intriguing dual nature, sometimes a wave, sometimes a particle. De Broglie took this idea a step further, proposing that if light, a wave, can behave like a particle, then perhaps particles, like electrons, protons, and even entire atoms, can also behave like waves. He called these matter waves. This wasn't just a philosophical musing. De Broglie provided a concrete mathematical relationship to describe this wave-like behavior of matter. He formulated an equation to calculate the wavelength of any particle. The De Broglie wavelength, denoted by lambda, is equal to Planck's constant h divided by the momentum p of the particle. In simpler terms, lambda equals h/p. This equation links the wave-like property, wavelength, to the particle-like property, momentum. Here, h is Planck's constant, a fundamental constant in quantum mechanics, and p is the momentum of the particle, which is simply its mass times its velocity. The smaller the momentum, the longer the wavelength, and vice versa. Now, you might be thinking, if everything has a wavelength, why don't we see everyday objects like baseballs or cars behaving like waves? The answer lies in the incredibly small value of Planck's constant. For macroscopic objects, their mass and velocity are so large that their momentum p is enormous. When you divide Planck's constant by such a large momentum, the resulting De Broglie wavelength is infinitesimally small, far too small to be observed. However, at the quantum level, where particles have extremely small masses and velocities, their momentum is tiny. This results in a De Broglie wavelength that is significant and measurable, making their wave-like properties observable. De Broglie's hypothesis was truly groundbreaking, but it remained a hypothesis until 1927, when it was experimentally confirmed by Clinton Davisson and Lester Germer. They observed electron diffraction patterns, similar to those produced by light waves, proving that electrons indeed behave like waves. This monumental experiment provided direct evidence for matter waves. De Broglie's hypothesis fundamentally reshaped quantum mechanics and opened the door to new technologies. It laid the foundation for the electron microscope, which uses the wave nature of electrons to image incredibly small objects, far beyond the capabilities of optical microscopes. De Broglie's hypothesis is a cornerstone of quantum physics, reminding us that the universe is far stranger and more fascinating than our everyday intuition suggests. It challenges our classical understanding of reality and highlights the beautiful, paradoxical nature of the quantum realm.